Thank you, ma'am. It's my great pleasure to introduce today's resource person, Dr. Krishna R. Reddy. Dr. Krishna R. Reddy is university scholar, distinguished researcher, and a professor of civil and environmental engineering. Dr. Reddy is the director of Sustainable Engineering Research Laboratory and also the director of Geotechnical and Geoenvironmental Engineering Laboratory in the Department of Civil and Materials Engineering at the University of Illinois at Chicago. Dr. Reddy received his PhD in civil engineering from the Illinois Institute of Technology, Chicago, USA. He received gold medals for being first in his class of BS Civil Engineering at Osmania University and MS Civil Engineering at IIT Roorkee. Dr. Reddy has over 28 years of research, teaching, and consulting experience within the broad fields of civil, geotechnical, materials, and environmental engineering, addressing the nexus among sustainability, resiliency, infrastructure, water, energy, and the environment. Dr. Reddy is the author of 4 major books, Geoenvironmental Engineering, Site Remediation, Waste Contaminant, and Emerging Waste Management Technologies. Sustainable Engineering, Drivers, Metric Tools and Applications, Sustainable Remediation of Contaminated Sites, and Electrochemical Remediation Technologies for Polluted Soils, Sediments, and Groundwater. Dr. Reddy has served or currently serves as an associate editor or editorial board member of over 10 different journals, including the ASCE, Journal of Geotechnical and Geoenvironmental Engineering, the ASTM Geotechnical Testing Journal, the ASCE Journal of Hazardous, Toxic and Radioactive Waste, the Journal of Hazardous Materials, among others. Dr. Reddy has received several awards for excellence in research and teaching, including ASCE Wesley W. Horner Award, ASTM Hagen-Togler Award, UIC Distinguished Researcher Award, University of Illinois Scholar Award, and University of Illinois Award for Excellence in Teaching. He is a Fellow of American Society of Civil Engineers, a Diplomate of Geotechnical Engineering, and a Board-Certified Environmental Engineer. He is also a Registered Professional Civil Engineer and an Envision Sustainability Professional. Thank you. Over to you, sir.
Good evening, everyone. Can you hear me?
Yes, sir, very much. And your slides are also visible.
Yeah, so good morning from here in Chicago. So the time here is 7:52 a.m. So I'm, as we speak, I'm having my coffee. And for you, it's evening. So good to join you. I just want to mention that I have another webinar to host at 6:45 my time. So I want to be a bit, quick on my presentation, and maybe I may not have enough time to answer the questions at the end, but I will be happy to answer them by email. So, I heard the first presentation, very useful, very technical. But in my case, I'm going to talk about this very broad topic in a more general sense. So hopefully, you will understand from my presentation what is sustainability, what is resiliency, and why those are important for design of civil infrastructure going into the future. So before I get started, I want to thank Narasimha.
So there is some disturbance. I'm sorry.
Section Southern Region President for his invitation. He is making this section very active. I also want to acknowledge these co-organizers for undertaking these kind of activities. And I want to thank my students, who have helped me to put this presentation together, or some of the framework that I'm going to present, is developed by these students. So I asked them to join, maybe, they are online, I'm not sure. So in my presentation, what I want to do is quickly,
sir, I'm sorry to interfere. I'm sorry to interfere, but there is some disturbance. Poloju, sir, are you mute, sir? Could you check muting? Yeah, now it's better, sir. There was some disturbance. Thank you. So please carry on, Dr. Reddy.
So yeah, I will give you a brief introduction to civil infrastructure, and many of you know, and I will introduce you to the terms sustainability and resiliency definitions, and then why we need to worry about these things, recently, and then how do we assess sustainability and resiliency, and then I'm going to briefly go over one of the frameworks that we developed recently. So I'm going to then show you a case study, and then I will close the presentation with the final remarks. So with respect to the buildings, when you talk about civil infrastructure, a lot of times, buildings come into picture. But civil infrastructure is more than buildings. So talk about roads, bridges, pipelines, railways, airports, dams, levees, and landfills. And not only that, we have to deal with water supplies, wastewater, power transmission lines, telecommunication lines. So the role of civil engineers is very essential for sustainable development. So our role is not just building the buildings, but we have to build all these kind of infrastructure. So that's what we need to keep in mind. In the US, every 4 years, ASCE looks at the existing infrastructure and comes up with the grades. These are the grades that have been given recently for the US infrastructure. As you see, our infrastructure in the US is considered good, or excellent. But in fact, if you look at a lot of engineering details, this infrastructure is getting aged, and it's not functioning efficiently. So there is emphasis for building new infrastructure in US. Also, all the infrastructure that was built in US, it did not consider the sustainability or environmental aspects. As you see from here, so, a lot of development that happened in the US is at the cost of a lot of ecological damage. As I mentioned, we didn't consider ecological and environmental damage when these were being built a long time ago. Didn't consider, energy efficiency, depletion of natural resources, increased waste generation, increased pollution, and we didn't consider greenhouse gases and climate change at that time. We didn't consider about resiliency. We didn't consider about life cycle sustainability. So there are a lot of things that are now, considered important or not considered at that time. So therefore, the infrastructure is not sustainable and resilient. So going into the future, we should be looking into this infrastructure development in a different way. So the problem with the current civil engineering practice is that we follow codes and regulatory requirements, and we design for technical safety. That's what we teach in our universities for students. And then when it comes to the real projects, we look at the design that is easy to construct, that costs less, and that takes less time for construction. So there's nothing wrong with these things. We have to be doing these things. But going into the future, we should be considering sustainability, life cycle thinking, resiliency. If you consider these things, we may be coming out with innovative solutions that are effective and economical and environmentally safe, and also contributes towards the sustainable development. So this is where our civil engineers need to be educated and do things in a way they are sustainable and resilient. So a lot of people know about sustainability. I just want to give a quick overview of this one. Sustainability, everybody knows about this definition: development that meets the needs of the present without compromising the ability of future generations to meet their own needs. I like this definition. It's very simple, succinct, and it conveys the message in a powerful way. However, it does not help us if you want to do something about sustainability. So that's when you need a functional definition for sustainability. ASCE has given this definition. This is a little bit wordy, but the main point in this definition is triple bottom line. So the triple bottom line will help us, to do something that can really contribute towards the sustainability, the broader definition that I showed you in the previous slide. And this definition, this functional definition can be applied at different scales. It could be small scale or large scale. So that's what we're going to use it in my framework. So when you talk about sustainability, the scale of sustainability projects can vary quite a bit. Global scale, as we speak, COP26 is going on in UK. And all the countries are thinking about how to cut down the greenhouse gases. So that's a global effort. And every country has their own plan, national scale plan, and even India has their renewable energy plan. Regional scale, you could have a state level or city level, or business or institution scale. You could have, sustainability assessments within the university or within the company that you're dealing with. But you could also have at a sustainable technology scale. And as engineers, in day-to-day activities, we should be able to contribute at this scale, if not, at all the scales. So ideally, you want to contribute at every scale. But however, on a day-to-day basis, you should be able to contribute at the sustainable technology scale. Now the question is, okay, I want to do things based on sustainability and resiliency. So what should I do? How do I, go about, incorporating the sustainability in my work? So this is where you need to, look at, okay, I designed something, and how can I say it's sustainable? So we need to have a quantitative framework to assess the sustainability. So many in civil engineering and in architecture, they know about LEED rating system. So this is for buildings. You get a rating of a platinum or gold or silver, based on what kind of environmental features are incorporated in the building. So this is good. This is one of the systems that can be used to design, green buildings. So the green buildings mainly consider only environmental aspects. And there is another framework or tool. It's called Envision. So since we have LEED for buildings, we don't have anything like that for assessing other types of infrastructure other than buildings. So this Institute for Sustainable Infrastructure, in association with ASCE, they came up with this Envision rating tool. Is similar to LEED. It has 5 categories, and then you have different credits, and then you look at each one of them and give the score. And then based on the score, you get different awards, just like LEED. So as you see here, there are 64 sustainability and resiliency indicators that you have to go through and give the rating, based on your project features. But when you look at the LEED is applicable for building, and Envision, if you want to apply it, it has to be like a really large project. And I'm showing these are the, the large project or overall project. But a lot of times, we want to look at, as an engineer, we may not be looking at the entire project, but we may not be even going for LEED rating or Envision rating. But on a day-to-day basis, I want to do, my work, and then I want to incorporate sustainability. So that's what I call it, project components. Let's say you're looking at the buildings. I'm a geotechnical engineer. I want to, design a sustainable foundation system. How do I do that? So you could have a regional stormwater management project, but I am a water resources person or environmental engineering person. I want to design the polluted stormwater treatment. So this, and then you may have a regional transport system, but I'm more interested as a highway engineer, looking at the pavement design. Or environmental engineer, I am more interested in decontamination technology. So what I'm trying to say is these LEED and Envision are applicable at a high level, project level. The scale is a little bit larger, but at the project component level, what can we do? So these are the projects that engineers deal with on day-to-day basis, and how can we ask them to incorporate sustainability in their design projects? How to promote this? So these are the things that I have been focusing on recently. So how do we consider the sustainability at the project component level? basically, from ASCE functional definition, we're going to look at this triple bottom line. So you need to look at, environmental aspects, economic aspects, and social aspects. But how do we quantify, sustainability of your project? So for that one, we need to define the SMART indicators for environmental, economic, and social. And indicators should be such that they will have some numerical value, metrics, and we should have some tools to calculate those metrics. So if we have, environmental indicators with numbers associated with them, economic indicators associated with them, social indicators, environment indicators, and numbers associated with them, then let's say, as an example, you have these environmental indicators, economic indicators, and social indicators. They're all in a numerical form, and then how do we can we combine them together to assess the sustainability? The other thing that civil engineers don't pay attention to is life cycle thinking. So we should be teaching our students, and also the project engineers should consider this life cycle thinking. So we need to think about, starting from mining, where raw materials are being acquired, manufacturing of the materials like cement and concrete, and how the construction is going on at the site, what equipment is being used, what are the gas consumption, and then what are the emissions, what are the maintenance issues, and then at the end of the project, what are we going to do with this one? So are we going to recycle the materials or just send them to the dump site? So all these different stages have to be thought out right in the beginning of the project. And we need to consider these triple bottom line aspects, environmental, economic, and societal aspects at every life cycle stage, and add them together to look at, overall, the sustainability of your project. So when you have all these indicators, right, you have environmental indicators, economic indicators, social indicators. So you are talking about these multiple aspects. How can we use all those aspects to calculate, let's say, sustainability index, like a one number instead of all these numbers? Can we calculate the sustainability index? So that's what we try to do in our framework called Qualix. So we use the multi-criteria decision analysis, such as MIVES and TOPSIS, and we also can weigh, differently different indicators. So this is an analytical hierarchy process or similar to that. And so we have a publication on this one. So I will be happy to send this publication if you are interested to get the more details about it. So we applied this framework for many projects, as I said, component level. So for example, we have a high-rise building, and then we have two types of deep foundations that are possible, and we could design those two types of foundations. One is the pile group, another one is a caisson or drill shaft. So we project engineers know this one. Even the students learn about how to design this in our foundation design classes. Now, both of them can function. Basically, they can support the column load, but which one is more sustainable? So applying this framework, you can calculate the sustainability index. So piles, having a low sustainability index, whereas caissons or drill shafts is having high sustainability index. So for this particular project, so the caissons are more sustainable. So that's why we should be recommending caissons from consideration, from sustainability considerations point of view. So this is the paper here at the bottom. You can get more details about how we did this analysis. So same thing, framework we applied in the environmental field. For example, if you have a groundwater contamination at a site, and to clean up that contamination, what are the technologies that could be applied? So we identified the 3 different technologies, and then we use this framework to calculate the overall sustainability index. As you can see from here, this technology, in situ chemical oxidation, came out to be more sustainable. So we have now a method by which you can assess the different options and come up with a more sustainable option. So just one more example of how to use the framework. For example, you have all these lakes and ponds, sediment at the bottom is contaminated. How do you clean it up? Again, this is one situation in the US. So we identified 4 different ways that can be, that can address the contamination. And then we subjected all these 4 of them to the sustainability assessment. We found out that modified capping would be the more sustainable option. So at least, you have a methodology, a framework by which, engineers can assess their options and suggest, something more sustainable. So from technical point of view, all options are good, but, from sustainability options, one, may be better than the other. So after developing the Qualix, recently we started looking at, developing a new framework. And in this one, we wanted to integrate the resiliency along with the sustainability. So the previous framework that I mentioned that considers only sustainability, that's a triple bottom line, environmental, economic, and social aspects. And we wanted to, add these resiliency aspects. And we wanted to make it such a way that, it can be applied to any life cycle stages or entire life cycle stage. And, also any project of any size. And we wanted to make it very flexible, and especially when it comes to the tools, whatever, tool or whatever the information that is available that could be useful in this framework. So if you insist on very rigorous quantitative methods, sometimes they may not exist. So this framework, we wanted to make it very flexible, tier-based selection of the tools with whatever information that is possible. So in this one, compared to the previous framework as at Qualix, so in the Qualix, we had environmental, social, and economic aspects, but resiliency was not there. Now we're introducing the resiliency in this one. So this is the overall framework. I will go into a little bit details on this one, but it provides a very, systematic roadmap on how you can accomplish, sustainability and resiliency in your designs. So this, we call it a TQLXR, and so that stands for Tiered Quantitative Assessment of Life Cycle Sustainability and Resiliency. TQLIZR, that's what we just call it. So there's a publication on this, and if you are interested, I can provide that one. So now the question is, a lot of people may be familiar with resiliency, but those students in the audience, if you know what resiliency is all about, coping, adapting, and growing in the face of uncertain and extreme impacts that may occur over the life cycle of the project. So if some unexpected thing happens, and then how would your design perform? So this resiliency can be explained, a little bit, better way using this sketch. So let's say you design something, but if something happens, for example, it could be earthquake, or it could be a cyclone, or it could be a lot of rain. So you're going to compromise the performance of your structure a little bit, but hopefully it does not collapse. And then when that event recedes, then your system should recover, maybe not at the same level as the original, but it should be functionable. Or you want to design such a way that it can come back to the original performance or even perform better. So we're talking about these things. Now the question is, what are these uncertain and extreme impacts? There could be different things, but the one that people are concerned about these days is global warming and global climate change due to increased greenhouse gases. That is causing a lot of the sea level rise, floods, droughts, wildfires, and so forth. So this, global climate change is due to greenhouse gas emissions, and as a result, the temperature is being increased globally. And as a result of that, we are seeing a lot of these climate change hazards. So these were not happening before. Now more and more are happening. So as a civil engineer, we are not used to consider these impacts. So now is the time we need to consider these impacts. For example, this picture you see here, a lot of flooding in Chennai, which was not common. I mean, even now you see, a lot of cities which were not prone to that much of flooding are being flooded, and we need to consider these things. So these climate impacts are, keep on increasing every year. So it is not an anomaly. We really need to be looking at, considering these impacts in our design. So currently, we don't have a course, we don't have, a university curriculum to address these things, but these are all things evolving, and you need to be on top of these things, going into the future. So the climate change, it's going to change the temperature conditions. They're not, constant all over the places. So every place has different conditions. Precipitation, rainfall changes are happening differently. Wind patterns are changing differently. Wildfires are happening differently. So these are the conditions that we need to account in our assessments. So coming back to this, our framework, we wanted to, as I said, we wanted to integrate the sustainability aspects, that environmental, economic, and social aspects, and also resiliency. So basically, coping up with this climate impacts. So how do we do that one? So just I want to go over this one very quickly and show you an example of how this framework could be applied. So this framework is divided into 4 phases. So I will go over those phases. And then, each phase has a different steps to follow. So let me go over each phase and briefly explain the different steps that we have in this one. So the phase 1 is about, understanding what are the design constraints that you have and performing vulnerability and risk assessment based on the hazard that you expected at the site. And then designing your structure to be resilient. So as you see from here, you define the project goal and scope. That's, always done in the first. And you define your preferences, what you want to see in your project, and what are the technical options that you have for that. And then, from that, you need to look at which technical options are resilient. So this is kind of the linear process, but each of these steps have to consider a lot of different things. Before going to the next step. So even in a project definition, goal and scope, you need to involve stakeholders. So who are the people who are going to be connected to the project? So you define the stakeholders and then engage them in the project. So you ask them, okay, this is the project. What are your preferences? So consider their feedback. And then you have a technical options. As an engineer, you are supposed to do this vulnerability assessment and risk assessment, because let's say I'm expecting a lot of flooding. So how my design is going to be affected by that. So that's the technical aspects. But in addition to that, we need to look at social aspects, environmental aspects, economic aspects due to that hazard, and also incorporating your technical design, how that influences this environmental, social, economic aspects. So if you are going to have a lot of damage due to flooding, people are going to be affected. There's going to be economic loss. There's going to be environmental loss. So by doing your technical design to be resilient, how these social aspects and environmental aspects, economic aspects are going to be improved. So those aspects need to be considered. So these are the aspects that civil engineers are not typically aware of it. So for this one, you need to have indicators and then tools to calculate the metrics, and then you have multi-criteria decision analysis, and then you can calculate resiliency index for your different options, and then again communicate with the stakeholders, and then based on their feedback, again define your preferences. So after that, you have these technical options, and then subjecting again these technical options to all these things. So for different technical options, you have a resiliency index. Based on that, you can think about which resilient design options you want to consider further. So this is the first step, and very important step that consider the resiliency. And this has become extremely important, because if you don't consider resiliency, whatever you design is not going to function in real life going into the future. So this provides a structured flow to include technical considerations, and also it considers all the different indicators, technical, environmental, social, and economic in an informed manner. So if you want to do something about resiliency, we are providing a roadmap on how to go about it. So the resilient design options are based on vulnerability and risk assessment, and this is something the students and project engineers have to know it. And then once knowing the vulnerability or risk, then we need to think about what can be done to minimize those risks. So you incorporate those adaptive measures and then redo the vulnerability assessment until your risk is less than acceptable. So we have this methodology, basically, do the vulnerability assessment, and then think about adaptive strategy, and then incorporate all that in the design. And then even when you construct it, you need to periodically monitor it and reevaluate and redo this vulnerability assessment, periodically to see if you are coping up with all the exposure scenarios, hazards that you anticipated in your assessment. Now, if you do that one, that's fine. But the question is, even after doing all these things, how resilient is your design, right? So this is where you need to calculate the resiliency index. So for this one, you need to calculate the hazard-related resiliency indicators and metrics. They could be technical, environmental, economic, and social. So they're all interlinked. So one could affect the other one. So you need to look at the interdependency of these indicators, and then you need to come up with the metrics. So that's a really challenging part. And if you have those metrics, similar to Qualix, we could do multi-criteria decision analysis and calculate the resiliency index. And the higher the resiliency index, better will be the project that will resist the expected future hazards. So now moving on to the second phase. Second phase is all about sustainability indicators and weightages. So what you have from the phase one is maybe 1, 2, 3, design options that are resilient. So you always have options. So maybe let's say you have 2 or 3 different resilient design options. Now what we want to do in the phase 2 is to do the sustainability assessment. For sustainability assessment, you need to define the indicators and then weightages. So the first step is to select which resilient design options you want to evaluate for sustainability. And then you need to define variables and that represent the problem. And then you have these requirements, criteria, indicators similar to Qualix. And so you have these triple bottom line aspects. And within that, in the criteria and indicators, we have environmental, social, and economic, as we had in Qualix, but we are adding these additional indicators, resilience. So what are the resilience-related environmental impacts? What is the resilience-related indicators for social? What are the resilience-related economic aspects? So those are all the indicators that we need from sustainability point of view, from this triple bottom line point of view. And then we can apply the weightages, because not all the factors may be equally important. Maybe that's the baseline condition. But if you have some specific requirements, you can assign the different weightages. You can make them equal or change them differently. How do you change these weighing factors? Sometimes you use analytical hierarchy process or some other processes, and so you get a weighing weightages for each of those indicators. So the whole idea of this phase 2 is to identify all the sustainability indicators and then and associated weightages. So once so going into a little bit of details about that one, as I mentioned, the indicators are these 4: environmental, economic, and social, and resilience. And you always have to consider the interconnectedness of those, because they're not all independent. So applying the weightages, as I just mentioned again, we may have to use analytical hierarchy process or something like that. And then, tier-based approach that we want to use it. And in the tier-based approach, I will mention those one a little later. Just you could have, three levels of tiers to accommodate whatever the information that you have. A lot of times, the information that you have is not enough. So a lot of times we may not be able to perform. So we wanted to make this framework flexible enough to use any information that you have and be able to perform this assessment. So in the in the third phase, what we do is we look at all those indicators, and we need to calculate those indicators using some tools. Here again, the tiered tools we came up with. So flexibility to use information whatever you have. So we have to get the indicator values, environmental indicators, social indicators, and economic indicators. We need to get those indicator values using these tools. And then, what tool level you are using, tier level that you're using for your tools. So tier 3 is more advanced tool. So then you don't have to worry too much about the accuracy. But if I'm using tier 1 or tier 2, then, you need to consider weighing less for those things. And then second step is to convert all these values of different units. For example, economic indicators are all in terms of the dollars, and the environmental indicators are all on in different units depending upon which environmental impact you're looking at it. So this establishing the value function for indicator is normalizing those values from 0 to 1, so that we can put everything, all the things. We can look at all of the things irrespective of their units. So then we need to do the perform sensitivity analysis and uncertainty analysis, because this is important, because all the numbers input that we use in this kind of analysis are not certain. Some of them could vary. So you need to look at how each of those input values, if you vary them, how sensitive is your output, and also uncertainty in the input. So some of them, they vary one value to the other value. So how do we address those uncertainties? This tells us what are the sensitive input parameters, and also how we address the uncertainty for the input that could vary in a range. And then we use the multi-criteria addition analysis, similar to Qualix, and then we calculate this sustainability resiliency index. Before in Qualix, we call sustainability index, but here we are incorporating resiliency, so we're calling this resiliency sustainability resilience index. So I already mentioned this one. These are the environmental, social, and economic. This is the criteria. Within the criteria, you have a resilience indicators. Resilience-related indicators, and what kind of tools that you're going to use for calculating that indicator. And finally, you have a values, indicator values for this. So these number of indicators really depends upon your project and information that is available. And in all these assessments, the challenging thing is to identify indicators and calculating those metrics. So for this one, you could have indicators qualitative or quantitative, but we need to have a flexible approach. Some of them can be quantified, some of them cannot be quantified. So we need to develop a system that is flexible. And then how do you quantify indicators numerically? This is the most challenging part. And what we did is we proposed a tiered approach. So the tier 1 is qualitative, basically best management practices. Tier 2 is semi-quantitative, kind of use the rating systems. You may have a scale, give the number based on that. And the tier 3 is more advanced, we call it quantitative. So in the tier 1 is best management practices. You look at those things. Okay, have you considered these best managed practice? Yes means, you give a score of 1. And if you say no, you didn't really do good jobs, right? I mean, you didn't really consider the best management practice that would have been good to increase the resiliency and sustainability. So you get 0. So basically, we can use the scale of 1 to 0 for different identified best management practices. And then, that way you can come up with the metrics for each of the indicators. So these are qualitative, but we have a number either 0 or 1 associated with that one. So the second one is the rating system. So this is more like semi-quantitative. You identify different indicators and you create a numerical scale. Maybe 4 is the best option, 1 is the least positive option, and then you give the scores for those indicators. And there are some tools like the semi-quantitative tools like I'm mentioning here. SSEM is one of them. Streamlined LCA is one of them. And then they need a little bit more information than the tier 1, but this is much better than the tier 1. Tier 3, you use the your project-specific quantitative data and methods, and generally we use the software and some mathematical models. For example, for environmental things, we use the life cycle assessment. You have computer softwares like CIMA Pro, Gabi, OpenLCA, and that needs the input, and you get detailed output in numerical terms. So this is the ideal situation. If you can identify the input data, and if you have a software and you can get detailed output, this would be the most preferred choice for doing the assessment. So the question is, we want to be able to do the tier 3 for every indicator, but that's not possible. We are providing the flexibility. You could use the tier 1, just use the best management practices. Tier 2 is the rating systems. Tier 3 is the most quantitative advanced option. So this framework is flexible to consider these different tiers and then still be able to perform this assessment. So we need to normalize all the indicators because they are in different units. So that's the approach that we followed in Qualix, kind of the same thing that we are using here. So we use a multi-criteria decision analysis. You could use any multi-criteria decision analysis. When you have multiple factors, how do you make the decision? So that's the kind of a fundamental goal of doing this one. And then, as I mentioned, we need to do the sensitivity and uncertainty analysis because the input numbers are fixed. So we need to look at uncertainty about these things. So then we need to calculate the sustainable resilience index. So similar to Qualix, we look at all the indicators and then weighing factors for criteria, for requirements, and for indicators, and then we calculate the final, we call it sustainable resiliency index. So now at the end, we make the final decision based on that sustainability index. So I'm bringing in always people who are concerned about that project, right? So we need to think about engaging the stakeholders who are the project, people who are involved in the project. It could be government, it could be the financial people, or it could be people affected by that. So we need to inform them about our results. So each option has this sustainable resiliency index, and then see pros and cons of those. You educate them, and finally you decide which technical design to implement. Basically, at the end, you are coming up with a recommendation that is acceptable to the stakeholders and is sustainable and it's resilient. So this is the final goal of this whole aspect. And it's not easy. Sometimes if you go the highest sustainability in resiliency index, project may not be selected for different reasons. Maybe the budget constraints, or social acceptance, or stakeholders preference. So we need to keep options open. Just we don't go strictly based on the calculations. So there are many applications that you can think of for this framework. We are excited about applying it to different projects, but it's not easy. You need to have data, methodologies, and assumptions. There is no standardized tool, so we're dealing with qualitative and semi-quantitative approaches sometimes, and rating systems could vary, and social impacts are the challenging ones to address. So but it's good to have a framework that can, if somebody wants to do something, it provides a structured methodology or pathway to follow. So just within a few minutes, I want to explain how this methodology can be applied, right? So because the methodology is there, but if you know how it can be applied, that makes it more meaningful. So in our campus, we have 3 buildings that are heated or cooled using the geothermal energy. So geothermal energy is becoming very common in the US. It's a good renewable energy. So we have, these 3 buildings on our campus, as you see here. These are all connected to the geothermal system. But, if you don't have a geothermal system, so you're going to use this conventional heating and cooling system that, everybody uses these days. So we are trying to avoid these conventional heating and cooling systems because they are using the fossil fuels. So going into addressing the climate change, we really need to use a lot of renewable energy. So these are 3 buildings. So what for geothermal energy, it is for heating and cooling. So you need to drill the boreholes. You need to run these, geothermal pipes. You basically circulate the water. So the temperature from the ground is transferred to the flowing water, and then you use the heat pumps to either, heat it up or cool your building. So for our 3 buildings, we have 64 boreholes going down to 550 feet each. So this is the diameter. These are all the details about the geothermal wells that we have. And then we can, create a material inventory of these systems, the geothermal system that you have. So here, what we are trying to do is compare, the sustainability and resiliency of these 2 systems using this new framework. So you have a geothermal framework, and then the convention. You have a geothermal system, and you have a conventional heating and cooling system. So looking at the phase 1, so you define what is your objective. So here we are trying to assess the geothermal system compared to the conventional system. Who are the stakeholders? It's university administration, students, faculty, and staff, or the people who are going to be affected by this project. And then, how do you engage them? So how do you get their feedback? So you have to follow different methods, the interviews, surveys, and workshops to get their feedback, and then do the vulnerability and risk assessment. And for this one, we also need for resiliency assessment, we need to have these resiliency indicators: technical, environmental, social, and economic. So again, looking at this, let's say, the hazard in Chicago, maybe the extreme heat. And then these are the criteria. These are the indicators that we looked at, technical, environmental, social, and economic. For example, in the technical, if you have extreme heat, maybe the geothermal energy is not sufficient to meet the energy demand. Or what happens if some equipment malfunctions? So these kind of technical issues, you can look at it. Environmental issues, what happens to the air circulation issues, or social, what happens, if you have extreme heat, this does not function. So what is the occupational comfort and economic, aspect? So if that doesn't work, you need to have a backup energy, emergency repair, so forth. So basically, you need to identify indicators. You need to, apply the weighing factors for those things, and then these values, indicators, are based on the rating system. So semi-quantitative, tier 2 level that is applied here. And then we apply multi-criteria addition analysis based on these indicators. And then you calculate the resiliency index. So the resiliency index that you calculate based on the phase 1 for conventional is this, and geothermal is this. So there's not much a difference between those two. So that indicates that, the technical design could be, made better to be more resilient. So you want to increase this resiliency index to be higher. So that's kind of a lesson learned. And maybe you can go back, if it was the project that is starting or proposed, then you can go back and look at your technical design and change it. The phase 2 is all about sustainability indicators and weightages. So here are all our environmental, economic, and social. These are the requirements. Within the criteria, before for sustainability assessment, we had only the environmental aspects, but we are looking at the resiliency of these environmental requirements. So again, economic, we are adding resiliency for economic and resiliency for social. So, that's how we are integrating sustainability factors, that these are the triple bottom lines, and with the resiliency. And then we need to have tools to calculate this one. Well, for environmental aspects, we use the life cycle assessment, which is advanced tool. That's like a tier 3. So these are all like, calculated more accurately. Resiliency, we use the quantitative, so rating tools. Direct costs, you can use the advanced tools to calculate them. So again, the social aspects are mostly based on the rating tools, tier 2 levels. So basically, we need to somehow calculate these indicator values based on that flexible tiered approach that we proposed. And then based on all these things, you can calculate a sustainable resiliency index. So because of a lot of sustainability aspects, you can see geothermal comes out to be higher with the sustainability resilience index compared to the conventional. But resiliency, built in is less, but sustainability is more. But overall, this is, highly, sustainable and resilient compared to the conventional system. So now, that's the phase 3, and then fourth is the decision making. So as I said, you do all these calculations, but you're not going to go strictly with the results that you get based on your framework calculations. There are a lot of other factors that go into the picture. For example, I think for this geothermal project, this was done many years ago, and at that time they were not sure whether the geothermal will work or not. So I think they ended up having conventional as a backup system. So you ended up with both systems, conventional and geothermal, which is obviously not ideal, if you want to do similar projects going into the future. So the decision making is always difficult, and you need to look at who are the stakeholders, what their preferences are. All the other factors come into the decision making. So this is my last slide. I just want to mention that I know I talked about a lot of things, and I've done a little bit faster than generally I present. But the takeaway points are these. So if you are a student, or if you are a faculty member, or if you are a project engineer, going into the future, we must consider sustainability and resiliency in engineering designs. And there's a lot of emphasis why we need to do this one. So if you want to do this one, you need to have some help, right? So these assessment tools will provide you, a structured flow or a structured methodology, how you can incorporate the technical, triple bottom line aspects, that environmental, economic, and social, and resiliency dimensions. So now engineers have assessment tools to use it to incorporate sustainability and resiliency. So our proposed, T-Equalizer is a new framework. We are excited about that one. We are going to try applying this framework to other, good case studies, specifically designed to test this, framework. So we will be getting more results. Maybe based on those assessments, maybe we may, need to change this one a little bit. So we will, we'll be pursuing that research into the future. The challenging part in doing any sustainability resiliency assessment is availability of data, methodologies, and all the assumptions that you make in this one. So currently, you don't have design codes that require you to incorporate sustainability and resiliency, but people are looking into that. ASCE is coming up with a sustainability standard, and more people will be looking into developing the standards. So, I'm sure that in few years, we will be required to look at the sustainability and resiliency design. So even if it is not required, we know that these are the right things to do. So it's our moral responsibility to incorporate these in our projects. So I want to end with a reference. So if you are interested in sustainable engineering, resiliency engineering, I recommend you to get hold of this book. This could be a good textbook if you want to teach a sustainable engineering class at the undergraduate level. So I want to also end the presentation with this announcement. We have a weekly webinar series on geo-environmental engineering on every Friday at 7:30 p.m. India time. So in 15 minutes, I have to start that presentation. That's why I was telling you in the beginning of the presentation that I need to rush it to get back to that hosting that webinar series. So if you are interested in any of these webinars, go to this website and you will find more details about it. There are a lot of interesting projects that are being presented in those webinars. So it will be very useful for faculty as well as students were interested in. So just I don't have much time to answer your questions, but I want to give you my contact information. It's a kreddy@uic.edu. So feel free to send me email with your questions. I will be very happy to answer your questions. As I said, I need to host that other webinar. I need to start it in 5 minutes, so I won't be available to answer your questions, but I will be very glad to answer your questions by email. And you can look at these websites. You can get more information about our research, our publications. And with that one, I want to end my presentation, and I want to thank everyone for attending, and I want to congratulate the organizers for taking up the programs like this and trying to educate our future generation. So thanks, everyone.
It's our responsibility to now. Thank you, sir. It's been a fortunate for us to, and a great opportunity for having heard from you. It's been a very, very beautiful session. You unfolded an entire framework of development of indicators and, in this developing the index and resilience framework. I think it was a very interesting session and a very detailed and exhaustive, explanation that a research scholar can directly, dive into and take it up. You've taken us through a very beautiful journey, sir. Thank you very much.
Thanks, everyone.
Thank you once again. So,
yeah, it worked perfectly, sir. That worked perfectly, sir.
There's some network problem, and Sir Narsimholoju, sir, is not able to. Some issue, some network issue.
Issues were concerning me that maybe I had a bandwidth issue. Yeah, there's only so much cable between here and India, and I don't know how much I can show it. So, okay.
There's some network problem with the Holoju sir's end. He's thanking our resource person, Professor Krishna Reddy, for the presentation. So we now move on to the vote of thanks. I call upon Dr. A.G. Krishna, Head of the Department of Civil Engineering, Malnad College of Engineering, Hassan, to deliver the vote of thanks. Over to you, sir.
Thank you, Professor Sumana Jayaprakash, inviting me to propose the vote of thanks. A very good evening to all of you. I wish you happy Deepavali to all of you. So indeed, it's my great pleasure to propose vote of thanks in this pleasant evening of this today's program. So first of all, my sincere thanks to Authority of ASCE, that is Engineer Narasimhachari Polaju, Honorable President, ASCE ISSR, and Dr. Bharat Ganesh, Secretary, ASCE ISSR, Dr. K. Vidya, Honorable Treasurer, ASCE ISSR. They have given us an opportunity to host this program. Today is a special day, that is ASCE 169th Anniversary Celebration Day. We are very fortunate enough to host this event, collaboratively organized by the ASCE India Section Southern Region, Mahendra College of Engineering, Namakkal, Malnad College of Engineering, Hassan, Karnataka. So, my special thanks to today's special guest, Professor Samadhiya, Indian Geological Society, New Delhi. Is a special guest speaker. That is inaugural speech. He covered a keynote about this entire program. So, thank you, sir. So, my special thanks to Sanjay Rana. This is a geophysicist, AFP Academy chairman. He delivered a overview of transport seismic test, and transport demography. So he covered the geophysics and its usage in civil engineering, understand more about working principle in engineering field, seismic activities such as vibration, all those things, animated video about shear waves and ray waves in the direction of the propagation. So importance of shear velocities, that is shear wave measurement in different approaches. So wonderful explanation about the cross-hole test and borehole test preparation, and he is beautifully explained about the cross-hole test and downhole test, and also about the tomography, that is more details about seismic tomography. So I thank you, sir. So my special thanks to Krishna Reddy. So he is a university scholar, distinguished research and professor, University of Illinois, Chicago, USA. He delivered a talk of assess sustainable and resilient civil infrastructure. He covered the sustainability and resilience. So beautifully explained about the problem with the current civil engineering practice. To explain the scale of sustainability project, the project component level sustainability assessment, life cycle thinking, and borehole details. All those things he is explaining beautifully. So it's an wonderful and beautiful the talk. So I thank you, sir. So I thank the management of the Mahendra College of Engineering, that is R. Rammohan Ravindranath, Executive Director, and Sri Ashoka Haganalli, Chairman, MTS Hassan, and also thank Dr. R. V. Mahendra Gowda, Principal, Mahendra College of Engineering, Dr. C. V. Venkatesh, Principal, MC Hassan. I thank you, sir. I thank the convener of this program, Dr. K. Vidya, Dr. C.T. Shivashankar, and also I thank program coordinator Shantaram, Dr. Vijay, Mr. Mani Shankar, Ms. Suganti, Ms. P. Sharada. So they have taken very much pain to organize this event. So thank you again. So the entire program is coined by none other than the President Engineer Narasimhachari Poloju, because of his contact in India and the entire globe to contact resource speaker in any kind. So my special thanks to Engineer Narasimhachari Poloju, President ASCE ISSR. So thank you, sir. So overall the program is successful by the participants, and the credit goes to the participants. So without their cooperation and support, the program would not be a success. So I thank you all the participants across the globe. The program was systematically and well narrated by the Professor Sumana Jayaprakash, so assistant professor in our civil department engineering, MC Hassan, and his backup team, Mr. NT Chetan Kumar, so Mr. Hemant, and Ms. Siri Hemant, Ms. Arpita, so Dr. Vijay. So I thank you all. So overall, to the success of the program, on behalf of the Malnad College of Engineering and Mahendra College of Engineering and ASCE, that is American Society of Civil Engineers, the credit goes to the entire team and excellent resource speakers to make the program a successful. So thank you, Anodal. Over to you, Sumana Jayaprakash.
Thank you, sir. Thank you all. And hereby we conclude the international webinars of today on structural and geo-confluence. We look forward to your participation.
Certification of appreciation. As a token of gratitude, on behalf of ASCE ISSR, Mahendra Engineering College Namakkal, Malnad College of Engineering Hassan, Indian Geotechnical Society, IEI Mysore Local Chapter, and ICI, that is Institution Innovation Council. So I would like to appreciate Professor Samadhiya, Narendra Kumar. So please accept our token of gratitude, sir. And also I request to please accept the certification appreciation to Dr. Sanjay Rana. Please accept our token of gratitude, sir. And also I request Professor Krishna Reddy as a token of gratitude. Please accept our certification appreciation, sir. Dr. Professor Krishna Reddy, please accept our token of gratitude as a certificate of appreciation, sir. So overall, so once again, I thank you all. So wish you happy Deepavali. So we are hearing a big sound around us. That is an explosive, that is pataki sound. We are hearing. So I wish you all once again. So thank you, Malnad sir. Thank you, madam.
Thank you, Dr. AGK, for delivering the vote of thanks. And thank you all the participants. We look forward for your participation in the forthcoming webinar. Thank you.
Hello. Hello.
Hello, sir.
Good evening.
Good evening, sir.
Hello. I'm audible?
Yes,
Hello.
yes, you are.
Yes, sir, I'm audible, sir.
I'm audible?
Yes, sir, you are.
That was a very good session. I'm thankful to all the organizations and thank you. And I will join your next program. And participant certificate, we will get it when, ma'am? We will get the participant certificates.
So we will another 7 to 15 days. We will send you a mail.
Then feedback form will be available, posted in the group.
Yeah, in chat box we will post.
Okay, thank you.
It has, sir, it has been posted in the chat box.
How chat box it has been posted?
Yeah, yes, sir.
Yes.
Okay, it will be posted in the group. I'm not able to open the chat box, so it will be produced in the group. Or we have to go to the chat.
Once again, we will share, sir.
Okay, thank you.
So, are you a registered participant, sir?
Yeah, I'm a registered participant.
Okay, okay, sir.
So all registered participants will get the certificate soon, sir. So Professor Vidya madam, authority of ASCE, can we leave?
Yes, sir, sure, sir. Thank you, sir. Thank you, ma'am.
Thank you, madam. Thank you.
Bye, ma'am.
Same here. Thank you, ma'am.
Thank you, ma'am. We will meet the next program on the 19th November.
Yes, sure, ma'am.
Bye.
Sure. Yeah, bye.
Bye, ma'am. Thank you, sir.
Thank you, madam.